Come on in, everyone. We have some time while everybody's logging in. If anybody has any questions, you can ask them now. Of course, you can also ask them afterwards. Before I forget, I want to let you know, hopefully you've already seen the email from Miss Raskovic, but she called me. She is not doing well, and she had to cancel class tonight. So there will be no lab tonight. I said, hopefully you'd already heard, because I know some of you, she told me most, if not all of you, are actually doing your online portion of your lecture, like in the building, the JC building somewhere. So maybe that saved your trip. I'm not sure. That's the case. If that's the case, or either if that's the case or not, actually, we decided we're going to try to open up a lab in future semesters for anybody that takes the online classes, so they can do them in one of our classrooms where the computers are, and use our bandwidth and all that good stuff. Might be a little more reliable for them. I'm not sure, but we'll see. Anybody have any questions? I'm about to yawn, about to sneeze, and probably some other stuff too. I don't know. No questions? All right, well, today we've got some neat stuff we're doing with chapter 27. This is magnetism. And in magnetism chapter, we have to deal with something called a magnetic field. Just like we had electric fields before, we have a magnetic field as well. And remember, a field is basically when you apply to each point in a particular region of space. Each point, say parenthesis x comma y comma z, that gives you an ordered triple that defines a point x, y, z in some coordinate system where you know where the origin is, the x-axis is, which way the x-axis points, which way the y-axis points, which way the z-axis points. Once you have that coordinate system decided upon, then you can label every point in space with a x comma y comma z, and that will unambiguously tell you exactly where in space you're talking about. Now, if you take each of those points for some portion of the space, not necessarily all of it, but it could be, and you assign to it a particular value, let's say the temperature at that particular point, then you have a field. In that case, for instance, where you actually measure the temperature for each parenthesis x comma y comma z close parenthesis, that would be a temperature field. It's a scalar field, and just like before, we did an electric field, which was a vector field, because in fact the vector, or the electric field, is a vector quantity. It has magnitude and direction. So to each ordered triple x parenthesis x comma y comma z close parenthesis, we assigned a magnitude and direction, or a I hat component, J hat component, K hat component, or a X hat component, Y hat component, K hat, or excuse me, Z hat component. Or we might have even done so in spherical coordinates or cylindrical coordinates. And spherical coordinates, you'd have a R hat, theta hat, and Z hat component, but generally all you have to do is define the R vector, because the R vector is R times R hat, and R hat is a function of theta and phi, so you actually know everything you need just from that. In the cylindrical coordinate system, you would have an R and a theta and a Z, basically. So anyways, that's what fields are. And in this chapter, we're going to start talking about the magnetic one, which is a little odd in that specifically magnetism acts quite different from other things you've dealt with. For instance, if you had, for instance, a charged particle sitting still, unlike an electric field, a magnetic field will apply no force to any charged particle sitting, say, on this pin. Okay, so even if we had a whole string of charged particles aligned along this pin, all of them positive or all of them negative or whatever, doesn't matter, the magnetic field of the Earth or any other magnetic field would not affect this charge whatsoever. Now, If instead, and I would ideally like to be using a point object, if instead we had this little, this little dot here, okay, so that's a little point charge. That point charge sitting perfectly still is experiencing no force from a magnetic field. However, as soon as that charge starts to have any velocity relative to the magnetic field, then the magnetic field applies a force to it. And it does so in an odd way. Specifically, if it's a charged particle, say it's positively charged and it's traveling, say, this way, then that's one direction. If the magnetic field is in fact acting in, let's say, the downward direction, okay, so the magnetic field is acting downward, the positive particle is going this way, then there's a right-hand rule where I used to use this thing where I do this, but I found that students seem to understand this one better. So this is our vector that would be represented by the charge of the particle times the velocity. So if the particle is positive, it's going to be parallel to the velocity. If the particle is negative, it'll be anti-parallel to the velocity. So this charge was positive, as we said. Then this vector is the B, the magnetic field. That's the symbol we use for the magnetic field. And then, since we're all oriented, this thumb sticking out tells us which direction the force would be applied. So in this case, if a charged particle is going this way and it's positively charged, the magnetic field points down, then the force on the actual charged particle would be right towards me. If, on the other hand, if the magnetic field came out towards me and the charged particle was this way, then the force would act upward. Okay. And that would tend to make it go up. And then, of course, you now see the force is still perpendicular to it. So that'd make it go up more, and that would make it go up more, and that would make it go up more, and that would make it go up more. And in fact, what it would do is tend to rotate like this. Now, if it also had a component, say, towards the screen, then only this component would actually be affecting it. And because it would be going up, like this and going in that circle, this other component is going to be unaffected. So it's going to spiral, even though the radius will stay the same, it's going to spiral into the screen. And that's some of the weirdness of the magnetic field. Some of the other magnetic field weirdness is the fact that if you have a bar magnet like this, where this is the north end of the bar magnet and this is the south end of the bar magnet, neat thing happens that when you cut a bar magnet in half, you don't get a separate north pole and a south pole. In fact, this piece of magnet will become a magnet by itself with a north pole and a south pole. And then this piece of the magnet will become a magnet by itself with this part being the north pole and the south pole. So that's something weird as well. We've known about this for literally thousands of years. The first stones that were attracted to each other, like literally you could pick up two stones and they'd stick together. You'd pull them apart and they jump back together again. Those stones were found in a place called Magnesia, which is roughly in what we now call Anatolia or Asia Minor, which is modern day Turkey. It's also roughly the area, if those of you who know about Paul of Tarsus, roughly that area where he was from as well. So those things were called magnets from being from the place called Magnesia, and that's where we get the name magnetism and so on. It turns out that magnetism is closely related to electricity, but we didn't really know that until the late 1800s, when people were doing Faraday and various other people were doing various experiments that ultimately led us to Maxwell discovering Maxwell's equations. Even though a large part of Maxwell's equations was Maxwell just literally reading the notebook of Faraday and taking his brilliant mind and translating it into the mathematics that his brilliant mind didn't have the tools to deal with, but it certainly had the intellectual capacity to imagine. And so a lot of the equations of Maxwell, or a good deal of the work, was just done by Faraday already. Other people obviously contributed, and some of the experiments Faraday had done were things that other people had done as well. But Maxwell did had to make some changes because there were some inconsistencies that he had to fix. So that's what we're going to do today, is talk about how magnets affect things, how they affect charges. And we're going to do so, in a physics way, where you're going to actually have equations that relate the force to the strength of the magnetic field and to the velocity of the charged particle and stuff like that. And even to, for instance, the length of a wire carrying charges, because imagine if this is a wire carrying positive charges this way, then yeah, each of those individual charges is experiencing a force from the magnetic field. Therefore, this whole wire can experience a force from the magnetic field. We're going to work all that out, but it requires some sort of weird mathematics to get things that require right-hand rules and stuff. There's some mathematics that you got to do with vectors to produce other vectors that are perpendicular to the original two vectors. Hopefully you guys know enough about trigonometry already to know basically what operation I'm talking about there. If you don't, it's not a big deal. We're going to show you that anyways. I will tell you that the magnetic field, we use a symbol B for it, capital B for the magnetic field. In engineering, sometimes they'll use an H or some other symbol. And sometimes they use H for something closely related to the magnetic field, but it's not quite the magnetic field. But the main thing is we use in physics the magnetic field symbol capital B, and the SI unit for the magnetic field is the Tesla, named after Nikola Tesla, who, if memory serves me, is from Serbia. I know he's from that portion of the world, and it's just a matter of, there were several little countries in there that we at one time had a little bit of a battle with, and ever since then I've sort of forgotten which one he's from, but I'm pretty confident he was from Serbia, and I don't mean to offend him by that, because he was really a brilliant person. If you choose to read something about him, just be aware there's a lot of kooky people in the world that believe a lot of kooky things about Tesla, and it's just rife with conspiracy theories and things like that. Because, for instance, Tesla really was looking for a way to sort of take the electrical energy from the earth and supply it to everybody sort of free, or at least he hoped there might be some way of doing so. So, of course, that just fed into people thinking, oh, somebody must have got to him and made him not do it or whatever. But in reality, what happened to poor Tesla was actually quite worse. So, like I said, as you read any biographies of them, just be aware that a lot of times the people that are writing it are they just believe some things that a lot of people believe. For instance, I read one one biographer. Her last name was Cheney. I think it was Margaret Cheney, no relation to the past vice president or anything like that, but her last name was Cheney. And she said, even though it was obvious that Tesla had magical powers, he did not personally believe so. So that's the kind of stuff you'll run into when you run into Tesla. Now, there was a big battle in the early 1900s. To give you some perspective, for instance, Tesla was a contemporary with Edison, Westinghouse, younger than them, of course, but also with Mark Twain, and I think quite a bit younger than him as well, and got to meet them and all that sort of stuff. And in fact, he came to New York with a letter from a friend of Edison's, and his friend, Edison's friend, had told him to go to New York and find Edison, and Edison will give him a job, more than likely, or something like that. So he literally goes to Edison's office literally like right off the boat, got his suitcase in his hand and everything, and waits all day. Finally, Edison sees him, and he introduces himself and hands a letter to him. He said, this is from such and such. And in the letter, it said, I've met two brilliant people in my life, you and this guy. So that was high praise from one of Edison's friends, but Edison didn't necessarily take it to heart like that guy really knew anything, because Edison was quite arrogant. But still, he said, well, I've got an outage in such and such a quarter in New York. So he's like in the process of powering New York City. So he sends Tesla out, who's come from Europe and probably hasn't seen anything like a power supply or power source company or something like that, a power producer. And he tells Tesla, well, if you can go out there and fix this problem, then I'll give you a job. Well, Tesla did it. So Tesla literally goes to this place to look at a power plant, probably some of which he's never seen before, and just fixes it and gets a job. He does a lot for Edison. Edison does a lot for him, but ultimately Edison ends up stealing a bunch of his patents. He gets lured away by Westinghouse. Westinghouse does a lot for him. He does a lot for Westinghouse, and then Westinghouse ends up stealing a lot of his patents. And then there's a big battle over powering New York, and Edison is shooting for powering it via DC, i.e. direct current. And Westinghouse, with Tesla's advice, is trying to say we should do it in AC. And in fact, Tesla's the reason that we now have 60 hertz AC electricity, because he's the one that really chose that setup, and Westinghouse won the battle. But it was really such an ugly time in history that Edison, in an attempt to scare people away from the horrors of AC electricity, literally put a elephant on display and exploded the elephant to show them how dangerous AC was, even though you could literally do the exact same thing with DC current. But it's just just a sad time. And obviously in the early 1900s and late 1800s, we had a whole different viewpoint on animals and life in general, obviously, because Edison, Westinghouse, and these people were probably well respected in the time, and to think that they would just haphazardly kill animals. Gary, Indiana did something like that as well, so you can read on that if you want. It's just some horrible things. Anyways, we have now an idea about what magnetism is. What I will tell you is I always had a hard time remembering which direction magnetic field lines point. Remember, we learned in the previous chapters that the electric field always pointed in the direction in which a positive charge would tend to go. So if you have a plus charge here and a minus charge here, that means you put a particle right here. If that's a positive particle, it tends to want to move towards the negative. So the electric field right in between those two must in fact point that way. That's the way the electric field direction is defined. In the case of the magnetic field, I use the analogy, and I don't mean any disrespect from this, but everybody knows a lot of people, as they get older, they retire and move down south. So I say magnetic field lines are like old people. They leave the north and enter the south. So if you picture a bar magnet, let's say this is a bar magnet, let's say this is the north. Well, the field lines, for starters, always make complete loops. So they'll go straight through the middle here and come out of the north end of the magnet, loop back around and come back in the south end of the magnet, and then go all the way through. That's the way magnetic field lines point. So if you want to draw an arrow, say right here, to represent the direction of the magnetic field, it would be roughly that direction, because it's pointing away from the north. Okay, so hopefully that'll help you a little bit. Now, in order for us to make some good use of stuff, I'm going to introduce a couple little things, specifically something called a cross product. And that's because some of the laws that we deal with are related to cross product. So let me start by sharing my screen and hoping that it works. So here we are. Mr. Younger just sitting here sharing the screen like he's a professional teacher or something. And boom, it worked. Wow, it's just the greatest time to be alive. Okay, so it turns out that, in fact, what I was telling you before was magnetic fields are like old people. They leave the north and go to the south. So let's imagine just for a second a bar magnet. So here's a bar magnet. Okay. And let's say here's the north end of the bar magnet and here's the south end of the bar magnet. Now, what I mean by that is, in fact, the magnetic field line leaves the north end of the magnet and comes back in the south end of the magnet like this. And in fact, it is a closed loop. In fact, basically one of Maxwell's equations tells us that magnetic fields lines have to make closed loops. They cannot just be randomly pointing out somewhere. For instance, you guys have learned about Gauss's law, and Gauss's law, at least in one form, was the closed integral of E dot dA equals Q enclosed over epsilon naught. And you remembered that Q was often equal to the integral of rho dV. Well, if you take Maxwell's equation and put it in differential form as opposed to this integral form, then you get something about like this. Okay. And what this thing on the left-hand side is a, well, for some reason, I know that in Portuguese, they call this upside down triangle a nabla, N-A-B-L-A. We call it a gradient, but you're actually doing a dot product of the electric field with a gradient. And the gradient we literally define, don't worry, I'm not testing you on this, but as I hat times the partial derivative with respect to x. Now that fancy symbol there, that's something that you haven't seen because you probably haven't had Calc 3 yet. All I can tell you is that it's really not very complicated. It's the derivative that you take of a function that has variables, let's say x, y, and z. Could have any number of variables, in fact. But what you do is all the variables other than x, you pretend like they're constants. So for instance, if you had a function f of x, y, z was 2 times x times y times z, the derivative of that with respect to x, the partial derivative of that with respect to x, would be treating the 2, the y, and the z as if they're constants. So you've got 3 constants times x. Obviously, the partial derivative of that would just be the product of the 3 constants. So you get 2 times y times z. So don't think about it any more than that. I'm not going to make you do anything with it. But anyways, then there's a j hat, a partial derivative with respect to y. And then there's a k hat times a partial derivative with respect to z. And you might notice that there's nothing for the derivative to take, right? It's just a derivative sitting there with nothing in the top part of the fraction. That's because it's meant to be put to the left, or excuse me, to the left of something. You can actually put it to the left of a scalar and you get what's called the gradient, which is sort of like a directional derivative that tells you the steepest direction to go. You can take a dot product of it with a vector like we're doing above, or you can take a cross product of it like a vector with it, like we'll see a little bit later. But the main thing is this quantity right here is called the divergence. And it tells you sort of how likely it is for some kind of field to be able to either, let's say, leave a particular point in space or actually enter a particular point in space. So if you have a field like this, obviously this is a field that has a lot of divergence. In this case, the right-hand side, this would be a lot of, say, negative divergence. And this one would have a lot of positive divergence because it's all these lines are diverging from that spot. In contrast, if you had a dot like this and your field was doing something like this, notice how all these vectors point along lines that are literally perpendicular to the lines that we drew earlier. This would be a divergenceless field. Okay. So the fact that we have quantity on the right-hand side of this Gauss's law tells us that you can actually have an electric field such that it leaves from some point and lands on another point. In fact, if you really wanted this left-hand diagram that I wrote positive under, all you have to do is put a positive charge right there in the center where that dot is, and that's exactly the electric field you get. When we write the exact same equation for the magnetic field, though, we get del dot B is equal to 0. So we can't have anything but closed loops. Okay, so again, I'm sort of tilting my hand showing you some of the higher order mathematics that goes into this, but the main reason is just to give you some understanding of why things are the way they are. We have searched very hard. No one's ever been able to find del dot B being anything other than 0. We've looked for magnetic monopoles, which is what a north end of a magnet would be if it didn't have a south end attached to it, or a south end of a magnet without a north end attached to it. Those would be magnetic monopoles. We've never found any, so we're pretty confident that they just don't exist. And as long as they don't exist, we're always going to have that particular part of Maxwell's equation. Both of these, by the way, Gauss's law and that del dot B are 2 of Maxwell's equations. Okay.
So what is B?
B is the magnetic field.
Okay.
So yeah, and that's actually good. That's what why I was trying to tell you all that earlier. So the magnetic field equals B, and I will say that the magnitude, or excuse me, the units of B are the Tesla. Now a Tesla is a big unit. For instance, a MRI that you use for checking whether or not your labrum of your shoulder is still intact, that MRI might use on the order of a 1.2, 1.5 Tesla magnet. That's super strong. Okay. The Earth's magnetic field is about a half a Gauss, and a Tesla is 10,000 Gauss. So 1 Tesla equals 10,000 Gauss. I didn't really look that up, by the way, so it wouldn't hurt if y'all double check me on that. But anyways, 1 Tesla is 10,000 Gauss, and the Earth's magnetic field's about a half a Gauss. So that gives you some idea of what this unit, the Tesla, is. And again, that is named after Nikola Tesla, who was actually, quite the character. I think he was on the order of like 6'5", and if you've ever seen any pictures of him, he was really skinny. So he might have weighed 150, 160 pounds at 6'5". But to make matters worse, he was just ready for any kind of cool electricity experiment or demonstration at any point in time. So he walked around with like 6-inch tall cork bottom shoes, not unlike what you might have seen pictures of Kiss doing back in the 70s and 80s, walking around with platform shoes. So imagine this, gangly character, 6'5" and 170 pounds, wearing a nice suit with tall curly hair like Lyle Lovett's, but wearing 6-inch cork bottom platform shoes. That's Nikola Tesla. And I definitely invite you to look up Tesla coils on YouTube and see. Tesla is the person that made up this Tesla coil, and you can see people creating huge lightning bolts that in some cases can strike over several meters. They've mounted them on top of cars before. One guy mounted one down in Australia, electrical engineer mounted one, made one himself and mounted it next to his pool, and then got in his pool with a chicken wire suit on and would allow the lightning bolts to strike him. So it's really cool. So check out Tesla coils if you want to see some cool stuff about what you can do with electricity. All right, so now here's the weird part. It turns out that when you have a charge Q and a velocity V, then the force acting on that charge Q with velocity V is given by this formula. So here's the formula. F, and I'll put a B on it just to remind you this is the force due to the magnetic field. This is Q times V. Remember, Q is a scalar. So when you multiply a scalar by a vector, the only thing it does is either lengthen the vector or shrink the vector. If the Q is bigger than 1, it's going to lengthen it. If the Q is less than 1, it's going to shrink it. And that's as long as it's positive. If it turns out to be negative, it's going to do the same thing, but it's also going to flip its direction by 180 degrees. So the force on the charge Q moving with velocity B is in fact equal to QV cross B. Okay. So that's the actual weird mathematical formula. Let me show you how we can go about calculating that. So let's imagine I'm going to draw a little coordinate system here. I'm going to draw a coordinate system. Okay. This is going to be my x-axis. This is going to be my y-axis. And this is going to be my z-axis. And let's say we're going to take a little particle right here. That's a particle of charge Q. Let's say that equals 1.00 times 10 to the negative 6 coulombs. And let's say that it is moving to the right with a velocity v is equal to, let's say, no, let's keep the numbers simple. Let's say 4.00 times 10 to the 5th meters per second j hat. Okay, that means it's moving parallel to the x-axis. Does that make sense to everybody? Okay, and let's say that there's a magnetic field B that is equal to, let's say, 2.00 Tesla, and it is in fact pointing in the negative x direction. So I'll put a negative right here and say it's in the I hat direction, but with a negative, that makes it the negative I hat direction. Okay. So there's a couple different ways you can do this calculation. I'm going to show you one here, and then I'll show you another, and then that'll be enough. Okay. So one way is you take the determinant of a matrix, and the matrix has to have the top row being I hat, J hat, and K hat. The middle row being Q times V. So you can see if I multiply 4 times 10 to the 5th times 1 times 10 to the negative 6, you're going to get 4 times 10 to the negative 1. So that'd be 0.400. And notice it's only in the J direction. I'm going to leave off the units. So I'll put a 0 here and a 0 there. Okay. So that middle row is QV. Does everybody agree that that's QV?
Is the velocity 4 times 10 to the negative 5?
The velocity is 4 times 10 to the positive 5. That's what made it be ultimately 10 to the negative 1.
Okay.
You see the Q is 10 to the negative 6. So that's why I did it that way. Now B, notice it only has a X component, and that's negative 2.00, and then 0 and 0. Okay. So the trick with this, and this is a way where you expand upon minors and this sort of thing. I don't really want to go over all that mathematics, but there's a rule that basically says you choose one of the items in the matrix, and you multiply that by the matrix that's left when you remove its row and its column. So for instance, if I chose to multiply by I hat, then it's in the first row in the first column, which means I'm going to now remove the first row in the first column of this matrix and take the derivative, or excuse me, take the determinant of the remaining 2 by 2 matrix. But when you do that, you also have to account for exactly which item you did that for. And since my item was the I hat, which is in the first row in the first column, I would raise -1 to the 1 + 1 power, and therefore it'd come out positive. And I'm doing 1 + 1 because it's in the first row in the first column. Whereas J is in the first row, but the second column. So that one would require a negative. And K is in the first row in the third column. That would make -1 parentheses to the third power. That's going to make a positive, so I don't have to do that weird thing. So the way I account for that weird negative is I just reverse the direction that I do multiplication. So you'll see as I go what I mean by that. So first off, I'm going to expand upon I hat. So I write down here, I write I hat. And now what that means is this row and this column are out of play. That leaves me that little 2 by 2 matrix in the corner. And in fact, what I have to do to take the determinant of a 2 by 2 matrix is I go top left to bottom right minus top right to bottom left. That's the way you do a determinant of a 2 by 2 matrix. So in this case, what I'm going to do is 0.4 times 0 minus 0 times 0. Okay. Now I do the next item. This time I'm going to expand on J. That means that this column and this row are off bounds. So I'm left with the 2 things in the left-hand side and the 2 things in the right-hand side. I'm going to put a J hat here. But remember, I told you that since this one had a row 1, column 2, the -1 would be raised to a third power, which is a negative number. So we'd actually have to multiply it by negative. So what I do to correct for that is I just do the determinant in the opposite order. So since I chose red to indicate that, what I'm going to do is say this guy is the minus, and this guy is the plus. So what I'll do here is I'll say 0 times -2 minus 0 times 0. So by doing it in that opposite order, notice I went from top right to bottom left first and called that positive. And then I went from top left to bottom right second and called that negative. That fixed my negative issue. So I'm good there. Now I'm going to expand upon K. And this one means I got to get rid of this column and this row. Okay. So I'll put plus K hat. I'll put the square bracket. Now I've just got the bottom left-hand 4. So I'm going to do my regular determinant for a 2 by 2, which is in this case 0 times 0, where I'm going basically from here to here. And then I'm going minus from here to here. Okay, so 0 times 0 minus, oops. Now I'm going to do minus 0.4. I'll leave off the extra digits just for the room, and minus 2. Again, leaving off the extra digits because of the room. Okay. So now you can see I've completed all of them. In fact, this part right here is just 0. This part right here is just 0. This part right here is just 0. But this part right here is in fact negative times a negative. That's plus 0.800. And in fact, the answer that we get is positive 0.800. And the units work out to be obviously Q times V times B. So that'd be a Coulomb meter Tesla per second, which is the same as saying positive 0. Oh, and I forgot a K hat there. So I better put that on there too. 0.800 newtons in the K hat direction. Okay. So that's one way you can do it. Now, obviously, that looks like a holy mess, right? But you can go back to the video and look at it bit by bit and make sense out of it so that it doesn't look so scary. But basically, all I was trying to show was that when I did I had basically the 0.4 and then down and to the right of it, the 0. I multiplied those first, and then I did the top left 0, which is right under the K hat, and the bottom left 0, or top right 0, excuse me, and then the bottom left 0, which was 2 below the J hat. And that's how I did that. That's why they're showing those black arrows there, and you can see a negative black symbol for the arrow going down to the left. Then when I did J, of course, I had to skip the middle column. So that meant I would normally go from top left to bottom right, but J was the one that causes it to be a negative. So I go from top right to bottom left. So I take the 0 that's directly under the K and multiply it by the -2 that's 2 under the I. And then I subtract from that the 0 right under the I and multiply that times the 0 that's 2 down from K. That's why I showed you in red. And then finally, when I got to the K hat, I used green. That took away the third column and the first row. So all I had left was the 4 that are under the I and J. And in this case, the K hat's a positive, so I don't need to do anything negative. I'm just going to go from the 0 under the I times the 0 2 down from the J minus the 0.4 under the J times the -2 2 under the I hat. So that's what all that was about. I'm going to show you another way in a second, but what I want to do first is realize, let you see that in fact the direction is exactly what we should have expected by doing the right-hand rule. So the right-hand rule, note you have to look at me in the little picture for a second, because I really need this diagram to stay up. The right-hand rule means you take your right hand and put it in this orientation, and then you make yourself understand that this finger, the index finger, is in fact at a 90-degree angle from the middle finger, and that the index finger is also at a 90-degree angle from the thumb, and that the thumb is at a 90-degree angle from the middle finger as well. Okay, so they're all three at middle. In other words, they make a X, Y, Z. X, Y, Z for right-handed coordinate systems. That's what they do. So if you point your index finger, so write this down probably, let your index finger point in the direction of Q times V. Index finger, direction of Q times V. Index finger, direction of Q times V. That means if Q is negative, you're going to put it the opposite direction of V. Okay. Your middle finger points in the direction of the magnetic field. Middle finger, direction of magnetic field. Middle finger, direction of the magnetic field. And then your thumb will point in the direction of the force. Your thumb will point in the direction of the force. your thumb will point in the direction of the force. Okay. So in our diagram that I have drawn here, I have my y-axis being parallel to my V, and I have my charge being positive, and the velocity points to the right. So I point my index finger to the right like this, to my right, which whatever it is for you guys seeing the screen reversed or whatever, that's the direction of QV. Now the magnetic field points into the page because the x-axis is supposed to be coming out, and I said it was in the -2 I hat direction, so it actually points towards the screen for me. That means the force is going to be in the upward direction, which is the k hat direction, and that's exactly what we got. We got positive 0.8 newtons in the k hat direction. Does everybody follow that now? Anybody have any questions on that? Okay, so that way is that is a good way of doing it. Notice with these two vectors, actually, these two vectors being perpendicular, really all you had to do was multiply 1 times 10 to the -6 times 4 times 10 to the 5th. That gives me 4 times 10 to the -1, and then times 2. That gives me 0.8. And then all I'd have to do is use my right-hand rule to tell me what direction it was. So you didn't necessarily, for this simple problem, have to do a cross product to get it. You just would know that the cross product would give you the direction by the right-hand rule, and that the magnitude, since Q and V and B are all perpendicular, well, not Q, then that makes obviously that you just multiply. So let me show you what you might have forgotten. So one thing, A cross B is equal to, as I just said, the determinant of A sub X, A sub Y, A sub Z, B sub X, B sub Y, B sub Z, I hat, J hat, K hat. And here's another one that you might not recall, but the magnitude of A cross B, remember that's a vector, is just the magnitude of A times the magnitude of B times the sine of the angle theta. And that is basically, if you put the vector A and the vector B tail to tail, then theta is the smallest angle between them. Okay. So the fact that the angle between V and B was 90 degrees is why I knew I could just do Q times V times B, because sine of 90 is 1. All right, with that in mind, let me show you the other way in case this one works better for you. And I'm going to do it on this nasty vector that I just drew. So A cross B is equal to, what I'm going to do is I'm going to write that same matrix. I'm going to write I hat, A sub X, B sub X, J hat, A sub Y, B sub Y, K hat, A sub Z, B sub Z, like that. Okay. Now, if I write that first two columns over again, I hat, A sub X, B sub X, and J hat, A sub Y, B sub Y, like that. Now I can immediately write the solution like this. Okay. I'm going to choose some really light colors here, specifically. I think that's a pretty good one, specifically so we can make sense of what we're doing. But basically, I'm going to go diagonally across, and then I'm going to go diagonally across, and then I'm going to go diagonally across, and these all three get added. Okay, so what that means is I hat times AY BZ plus J hat times AZ BX plus K hat times AXBY. Okay. Now what I'm going to do is I'm going to change colors, and let's use this putrid pinky looking color. I'm going to do the same thing, but this time I'm going to subtract all these. So I'm going to go diagonally down and to the left, and I'm going to subtract that. I'm going to subtract that, and I'm going to subtract that. So what I get is minus K hat AY BX minus I hat AZBY and minus, minus J hat times AXBZ. Now I can go ahead and write this a little simpler by grouping up the I hats. And what I'll see is I get AYBX, or excuse me, BZ minus AZBY I hat plus, that takes care of this term and this term, plus I get AZBX minus AXBZ. So that should take care of this term and this term. And actually, let me make this Z look a little better. Okay. And that's my J hat term. And then finally, I'll do plus AXBY minus AYBX. And that's all in the K hat direction. So that's a complete formula. You could write that down. You could memorize it, whatever you want to do. I have never, ever committed that to memory. I've always done it usually by working out the matrix in my head. But then when I got to basically the equivalent of calculus on manifolds, I found a quick and easy way that is not quick and easy for people that haven't done the Einstein summation convention. That's why I don't teach it to you. But I found a quick and easy way to do it component by component, so it's a lot easier. But basically, I went for over a decade, or well, almost a decade, I guess, doing it by just picturing the matrix in my head. Anybody have any questions on that? Okay, so that's a new thing of mathematics. Hopefully you all covered this before. Have any of you never seen a cross product like from trig or anything? Because I hoped everybody had actually seen one before, but that's not always the case, and that's okay. I mean, it's just a new thing to do. Remember, basically the cross product, we use it in physics whenever we're trying to get a vector component that's perpendicular to another vector. So for instance, in engineering, when you're trying to calculate a moment, what you care about is the vector component that's perpendicular to the lever arm. And therefore you can take the cross product of R, which is the lever arm vector, with F, which is the force vector, and that will give you just the component of R perpendicular to F multiplied by F, or the component of F perpendicular to R multiplied by R. There also happens to be a dot product, which hopefully you covered last semester, and that's also called the scalar product, because it actually spits out a scalar, and the scalar is the magnitude of A times the magnitude of B times the cosine of the angle between them. That one picks out light components. So like we used that one when we were doing work, because we wanted the component of force that was actually parallel to the motion. So when you take a dot product, you get the component of A, say, that's parallel to B times B. Now we also get, this is the part you might not remember, we also get AX BX plus AY BY plus AZ BZ. So this is just like what I just finished showing you for the cross product. Specifically, I showed you that nasty formula with all the minuses and all that stuff. And then I showed you A times B times the sine of theta. Well, I just did the same thing for the dot product. I did A times B times the cosine of theta, and then this ugly formula. Well, I've also done for the cross product that, and of course, this guy, which is A cross B, and that vector, or excuse me, that box goes like this. Okay. So now you have the formulae, LAE, say, of dot products and cross products. Any questions on those? Now, like I said, a lot of times you can get away with doing these calculations of force without actually doing the cross product. So I don't want you wasting time doing cross products if they're simple vectors that are automatically perpendicular to each other. Unless you just want it for practice with calculating cross products and dot products, then by all means, do 10 or 15 of them so you can get the hang of it. Once you've gotten the hang of it, maybe do one a week or something like that, you'll be golden. Now that we have that, I'm going to show you yet another reason that we have that. It turns out, in fact, that the force that a magnetic field applies to a wire carrying a current is, in fact, the current I times a vector along the wire whose length is equal to the length of the wire and whose direction is parallel to the current, crossed with the magnetic field. So again, we get another cross product. In this case, I'm going to stop sharing for a second so we can talk about our right-hand rule. It looks like I missed a chat. Thank you. Someone did confirm that I remembered correctly. 1 Tesla does equal 10,000 Gauss. Thanks for that, James. So I've been telling everybody use this right-hand rule, and that works fine. So the first vector in the cross product is always this finger. The second vector in the cross product is this, and the answer is the thumb. So in IDL cross B, you take the magnitude of I times the length of the wire, and that's the length of the vector IL, and you lay your finger, your index finger, in the direction of the current carrying wire in the direction of the current. And then you adjust your hand until the middle finger points in the same direction as the magnetic field. So if in fact, if the current carrying wire is carrying current directly into your screen, into my screen, and the magnetic field is going this way, then that's telling me that the wire is going to feel a force upward. And in fact, it would cause the wire to bend up a little bit. So that's how the right-hand rule works. I've also done it like this. I imagine this finger right here as if it's just one long bone, and I put that across the along the first vector. So A cross B, this would be A. And then I orient my hand. Remember, this thing is like an axle that happens to correspond with the vector A. I can't do anything with that other than rotate my hand like this, because I've got to keep this one long straight bone, which isn't reality, but it's what we're pretending. This long straight bone has to lie along A, pointing in the direction of A. So the only freedom I have now is rotating about that like it's an axle. I do that until my fingers can curl towards B. Let's say B points up, in which case I'd have to turn my hand, turn my hand, and then now I can curl my fingers towards B. Because of that, I know that the force in that case is the direction of my thumb. So that's another right hand rule version you could use. If you found that one more comfortable, then by all means use it. If you don't, throw it out, throw it out. Just don't even put it in your mind anymore. Okay. All right. So those are two of the cross products, right hand rules we're using. There's one more major one that's kind of helpful. And for it, we're going to see that we need a special vector, and I'm going to derive that special vector for you in a little bit. But if you have a current carrying wire, so let's say this pencil's a wire, and current is actually, and this is conventional current, so we're talking about positive charges shooting out there, okay? I'm supposed to, if I want to find the electric field caused by this, or excuse me, the magnetic field caused by this current, I'm supposed to take my right hand and point my thumb in the direction of the current and then curl my fingers around. Those fingers curl in the direction of the magnetic field. So let me share my screen real quick. So if you want to find the magnetic field going around a current, what we do is we imagine when something's going into the page, it's like you're looking at the back of an arrow, like, you know, a bow and arrow where it has a little feather on the back. So what I could do is I'd say, all right, well, this right here is a current carrying wire. And in fact, the current is going into the page. According to the right-hand rule, I stick my right thumb into the page and then my right fingers curl around in such a way that the magnetic field right here points that way. Right here, the magnetic field points this way. Right here, the magnetic field points this way. And right here, the magnetic field points that way. And then I can go in between and say the magnetic field points that way and that way and that way and that way. You'll see it's actually always perpendicular to the radial line. So if I drew, for instance, a radial line from, let's do it in a pink. If I drew a radial line to each of these, it would be perpendicular to it. So that B direction is what's shown by these little vectors. And in fact, these are all supposed to be at 90-degree angles, even though they're not perfectly drawn. Okay. So that's the direction that a magnetic field around a current carrying wire works. So let's use, I'm going to jump in and just do the hardest problem we possibly can for this IL cross B. That's also called the F equals Bill equation. So what I'm going to do is I'm going to set up a coordinate system just like this. Okay. This is going to be my x-axis. This is going to be my y-axis. I am going to have a current carrying wire, let's say coming in. Whoa, I didn't want that color. Go away. Okay. So I'm going to have a current carrying wire going into right here. Okay. And then it's going to be going out right here. So what do I mean by that? I mean that current is going this way and this way. And now the current carrying wire is in fact going to go that was not what I had planned. And it's also supposed to be this. Okay, that's supposed to be a perfect circle, but my stupid program doesn't know any better. So I'm going to attempt to draw my own circle. That's not so bad. Okay. Now, what this means is the current is in fact going this way as well. And what I'm going to do is I am going to say that there exists a magnetic field that is constant more or less throughout. And I'm going to say it's uniform. And it's going into the page. And it only exists basically, I drew that last one in a bad spot. And it only exists near that curved part of the wire. In other words, it doesn't exist on the straight parts that you see to the left and to the right, which is really convenient because I don't want to mess with that. Okay, so these are all magnetic fields going into the board or into page. Okay, and what I want to calculate is what is the total force okay. So what I'm going to do is I'm going to discretize, if you will, the equation I have. So I'm going to say dF is equal to the integral of I dl. Well, actually, dF will just be I dl cross B. Okay. So what I'm going to do is I'm going to first off imagine this being out at some angle theta. And then I'm going to allow this line to move by a infinitesimal amount d theta. And that's going to, in fact, give me a differential line element dl, which is actually equal to, and I didn't define this yet, but it's going to be capital R times d theta. And that's because I'm saying the radius from here to here is capital R. Now, that says a vector symbol, so I'm just going to write here, and I'm going to do it in red so you'll notice it. That's going to point in what I call the theta hat direction. Okay. So I'm going to take a second and just explain to you what that means, because it's super, 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 super convenient to be able to have such a unit vector. So if I take, for instance, the x-axis and the y-axis, and I pick a point in space, say right here, that point would be x comma y. But you know, in polar coordinates is also r comma theta. So you know this angle right here is theta. Well, it turns out you can redraw your x-axis and your y-axis, and then you can define a neat little unit vector that's parallel to that line we just drew, and that's called r hat. And then perpendicular to it and pointing in the direction of increasing theta, you can define another one called theta hat. Okay. And though it doesn't look like it because I screwed up a little bit, they're at 90-degree angles to each other. But you can see, in fact, that this angle right here is theta, and this angle right here is theta. And from that, I think you can see that r hat, remember the hat, does anybody recall what a hat means on a vector? What that little TP looking thing means?
It's a unit vector.
Exactly. So that means its length is 1. So if you imagine this little triangle right here, let me change colors just to keep it real here. If you imagine this little triangle right here, the hypotenuse is actually 1. So that tells you the x component of r hat is just 1 times cosine theta. Whoa, I didn't mean to write that in black. I'm going to say cosine theta, and that's going to point in the I hat direction. And I think you see that 1 times sine theta would be the y component. Not only that, I think you can look at theta hat now and convince yourself that theta hat is, in fact, the x component is going to be a -1 times the sine of theta. Do y'all see that? It's negative because it's pointing to the left. It's sine theta because it's, across from the angle theta. And then the y component is, anybody want to take a guess on that? So there's that vector and that vector. I've already done the one that's going to the left. That's the little pink one. So what are we going to do to find the vertical one? How about cosine theta? J hat. So that's really what that vector is, just so you'll know. And as you can tell by looking, for instance, at the current carrying wire, you can see that theta hat, if you multiplied it by a negative, you get exactly the direction of the magnetic field that we did for the current carrying wire. So you can see already why that vector is helpful. Now I'm going to go ahead and compute what F is. So let's go like I was with the black. I will say F is equal to the integral of df, which equals the integral of I, because what we're understanding is the current going through this is I, and the magnetic field in this is B, okay? So it's I times R d theta, theta hat, crossed with, and if you look at this, you'd say a right-handed coordinate system would have a k hat pointing out of the screen. The z-axis has to point out of the screen. So the B is actually in the negative k hat direction. So I'd say negative B, which is just a constant, k hat. Okay. Now that means I can take the negative I, the R, and the B. I'll say negative IBR, pull that completely out in front and say I'm going to take the integral of d theta times theta hat cross k hat. Now, technically, even though I wrote it to the right of d theta, you're actually integrating that too. Can anybody look at, let's say, the diagram that I drew in showing you r hat and theta hat? Can anybody use that to tell me which direction theta hat cross k hat's in? Or can anybody at least tell me what the magnitude of theta hat cos k hat is?
Is it 90 degrees?
Yeah, it's going to be 90 degrees to both of those, but is it going to be, well, which 90 degrees is going to be? And do you see what the magnitude is?
Magnitude's just one, right?
Exactly. Good job. Because it's the magnitude of theta times the magnitude of theta hat times the magnitude of k hat, which is the 1 times the 1 times this sine of the angle between them, which is of course 90, and sine of 90 is 1. So remember, you can use your right hand rule. You want your index finger to point in the direction of theta hat. And then remember, Z is pointing out of the page. So you want your middle finger pointing in the direction of Z hat, because that's the direction of K hat, right? And which direction is your thumb pointing now? Index finger in the direction of theta hat. Middle finger at 90 degrees like this. Okay. That should be pointing out of the page. And what direction now is your finger? Again, use this diagram that I did to show you R hat, theta hat. Okay. In the interest of time, I'm going to go ahead and tell you it's in the R hat direction. Okay. My index finger went this way.
Would it be in the negative R hat direction?
Not with your right hand, it wouldn't. You might have accidentally did your left hand. Oh, all right. Well, actually, are you using negative K hat or using positive? Because notice I pulled my negative out in front.
Oh, okay.
So I pulled my negative out in front, so I just had theta hat cross K hat. So that should point out. So with that being said, what we have now is the integral of, remember I told you, even though I wrote it to the right of the d theta, it still goes inside. So I'm going to integrate from theta equals 0 to pi of r hat, which we said was cosine theta I hat plus sine theta j hat d theta. And remember, I hats and j hats just get to come out in front and never have to play any calculus role when you're doing, oops, I meant to take the eraser and I grabbed the pen. When you're doing integrals and derivatives, the I hat and j hat are actual constant vectors. Okay. So I now have that IBR negative. Now, if you remember the graphs of sine and cosine, that would come in super handy here. For instance, cosine goes like, stupid thing. I hate it when it autocorrects stupidly. Like that, that's cosine. So if you go to pi, which is right here, I think you can see that this, despite my bad drawing, is in fact 0. And if you look at sine, ooh, that should have been like this, sorry. If you look at sine theta, you can see that in fact it does not go to 0 when you integrate it. In fact, it's going to be just the area under that curve. You can also tell that from a symmetry standpoint. Obviously, you're going to have a component of the force in the r hat direction, which means the r hat is going to have an x component, which points to the right for the right-hand side, and has a x component, which points to the left for the left-hand side. So you expect the actual left-hand components and the right-hand components to cancel each other out, leaving just a j hat component, and that's what we're doing. So mathematically, you can work it out and do it, but we know physically it's going to work out, and we already know mathematically that it's going to work out. So I'm just going to integrate sine theta, d theta from 0 to pi. And of course, the derivative of cosine is negative sine. So the integral of sine is negative cosine. So I'm going to go ahead and put, and don't forget everybody, Miss Rakovich said she's not coming tonight to lab, so you don't have to do that. I'm going to say negative IBR times negative cosine theta from 0 to pi. And of course, that's all times the j hat direction, which is equal to positive IBR times, in other words, I got rid of the negative. So cosine of pi is in fact equal to 0. Ooh. No, cosine of pi is equal to -1. And then minus the cosine of 0, which is +1. And then times j hat. So I ultimately get -2 IBR j hat is equal to the force. That's it. Easy peasy, right? Now look over the version. Your book does a similar problem. Look over the way they do it. You might find that better. Look over the way I did it. Watch this video, this part of the video a couple times. See if you can figure it out. You got to make some kind of peace with this. You got to figure out how to do this. I've sort of tried to show you all the parts that mathematically is going on. That's not necessarily the most helpful thing for some people, and for other people, it really is the most helpful thing. So your book author does it with some sort of trickery. In some sense, he does it with a little bit of physics trickery, which I think you guys are not that experienced at and might find that difficult. And then in other parts, he does it with some mathematical trickery, which I would think, having finished Calc 1 and well into Calc 2 now, chances are you've probably are a little bit better at mathematics trickery than you are at physics trickery. So I've found this to help, and I've been doing it for some time, and the students tend to do pretty well. Even though this, and for instance, that integration of Coulomb's law, and later the law of Biot-Savart, those are the hardest things that my students have to do every semester in the 242 equivalent course. But still, they generally get it. So it just takes a little while. Anybody have any questions on this? Because time is definitely up. Again, y'all do not have lab tonight, so you need not rush off because of that. But you might want to rush off for other reasons. But I'm going to wait for the last person to leave in case anybody has any questions. Other than that, you guys are free to go.
Have a good day.
You too. Thanks for coming. No other questions? Nobody? Esther, how about you? Any questions? Looks like you're the last one here. All right. Well, I'm going to take that to mean that you're possibly not here. So everybody have a good day. Thanks for coming. I'll be posting this shortly.